Now we'll finish up section 1.9, finish up chapter 1. And we left off having just described in particular in note 1.9.3 precisely how a presentation of a group leads to a group using free groups. And we had defined presentation as the last thing in the videos. So let's explore some implications of that definition. Now, notes 1, 2, and 3, 1.9.1 through 3, show us that if we have any sets X and Y, they result in a group G, including even set Y could be empty, as we'll see. Hungerford says that G, the group that results from a presentation of set X of generators and set Y determining the relations. This group is, quote, the largest possible such group in the sense, close quote, given in the following theorem. So we're going to state von Dijk's theorem. The theorem involves an onto homomorphism, and merely the fact that it's an onto function from one set to another has a cardinality implication. And that cardinality implication is if we have a mapping from set G to set H, that's an onto function, then this is a cardinality relationship that holds the very definition of cardinalities being greater than or equal to, in fact. So we'll be dealing with an onto homomorphism. It'll have the implication that for G, the group given by the presentation as described above, versus group H, any group which is generated by the same set of elements and has the same set of relations holding, will be less than or equal to in cardinality to group G. So von Dijk's theorem, theorem 1.9.5 says, let X be a set, let Y be a set of reduced words on set X, reduced in the sense described above, and G, the group defined by the generators, X in set X, and the relations W equals the identity for W in set Y. Remember, set Y was reduced words. We were ultimately interested in relations, but those relations have been presented in the group presentation always of this form. Take the elements of set Y and set them equal to an identity, the identity. If H is any group such that H is generated by X and H satisfies these relations, then there is an epimorphism mapping G to H. So we start with G is the group given by the presentation. H is any other group satisfying the same conditions as given in the presentation. Then there's an epimorphism mapping G to H. That is, G is bigger than group H in a sense. Careful with the bigger than, less than ideas if we happen to be dealing with infinite cardinal numbers. But it specifically means what's stated in terms of the onto mapping. Let's look at a proof of that, not very long. So here's a statement, and the plan is to find specifically this epimorphism. So let F be the free group on X. Then, as we saw in the proof previously, the inclusion map iota takes set X into H, induces an epimorphism, phi, mapping the free group into H. All right, so we got the epimorphism, goes from the free group into H. We need to concern ourselves now with the relations and the generators. Since the relations W equals E hold for all W and Y, then, as we saw in the previous note, that means W is in the kernel of phi. This holds for everything in set Y, reduced words, so it must be that Y is a subset of the kernel of phi. Hungerford feels compelled to point out we're treating the elements of Y both as words on set X and as products of elements of group H in this setting. The generators I kind of think of as letters, and set Y contains products of those letters, as it were. It contains reduced words, which ultimately are, we interpret it as products reduced in a particular way. So if we look at the normal subgroup N generated by Y in F, so we have first, Y is a collection of reduced words. So indeed, it's a subset of the free group. When we speak of a normal subgroup generated by a set of elements in a group setting, that's simply the intersection of all normal subgroups containing that set of elements. Definition of normal subgroup generated by a set of elements. Actually quite similar to just regular old group generated by a set of elements, subgroup in a particular group setting. So the claim is, let N be the subgroup generated by this set Y. It's contained in the kernel of phi. That is, N is a subset of the kernel of phi. Okay, let's chat about that briefly. Well, now the kernel of phi is a normal subgroup of group F. Kernels of homomorphisms are normal subgroups. We've used that many times. So here we have kernel of phi, a normal subgroup, and it contains set Y. So when I intersect all of the normal subgroups that contain set Y to create normal subgroup capital N, kernel of phi is one of those subgroups in that intersection, and that's where we get the subgroup relationship. So this group N generated by set Y is a subgroup with a kernel of phi. Equivalently, if we apply phi to the set N, then we get a homomorphic image of a group as a group. We get phi of N as a subgroup of the trivial group in H. So we're mapping phi maps F into H. So here we're using 0 to indicate the identity in the group H. So we have a subgroup of the trivial group. Of course, you know what that is. It's non-empty, so we've got the trivial group. It equals phi of N. Phi maps F to H as an epimorphism. We got that from corollary 1.9.3. Here we have a setting where, I'm going to run and look at corollary 1.5.8 here in a second to make sense out of this. But we have N as a normal subgroup of F. Epimorphism phi maps F to H. Here's H, and we have a normal subgroup of H, the trivial subgroup. And phi of N is a subgroup of 0. Phi of this subgroup over here is a subgroup over there of this normal subgroup. Let's look at corollary 1.5.8. We're going to use that to justify the existence of a homomorphism psi mapping quotient groups. So we're going to claim such a phi mapping one group to another induces a homomorphism psi mapping one quotient group into another quotient group. So let's step aside briefly to look at 1.5.8. So here we've got F mapping G into H, a homomorphism of groups. Okay, so this was the phi function. This was the F free group. N is a normal subgroup of G, and we had N as a normal subgroup of free group F. M is a subgroup of H. Yeah, well, we took the trivial subgroup. That's a normal subgroup. And hypotheses needed here are F of N is a subgroup of M. F of this normal subgroup is a subgroup of that normal subgroup M. And we had that as well. We had F of N was a subgroup of the trivial subgroup. So I wrote it the way I did in the notes. Hungerford wrote it that way, I trust, to make it line up exactly with this corollary 1.5.8. And it says then that homomorphism, phi for us, induces a homomorphism, let's denote it psi, that maps the quotient group G mod N, F mod N for us, to the quotient group H mod M, H mod the trivial subgroup for us. So we're applying this. In fact, there's a little bit more to the statement. That homomorphism, we'll denote it psi, maps left coset an in this quotient group to the left coset f of a m in this quotient group. So this gives us the existence of such a mapping. The next statement gives us a property of it. We're going to use both of those. So corollary 1.5.8 says phi induces a homomorphism psi mapping one quotient group into the other quotient group. F mod n into H mod the trivial subgroup. G mod n into H mod m in the notation of corollary 1.5.8. And this is exactly the conditions we needed. So that's why this little statement here. So that gives us the existence of the homomorphism we saw in corollary 1.5.8. We know a little property of how it maps particular cosets. So let's take a look at that part. For coset an in the quotient group F mod n, we have, as we saw in the corollary, that psi of an will be phi of a applied to subgroup, the trivial subgroup, subgroup M. This was f of a m in corollary 1.5.8. That's how the symbols line up. So here's how we have mapping psi behaving on those quotient groups. Phi's onto group H. Well, if phi is onto group H, then we produce here as A ranges over all of group F, we'll produce all elements of group H here onto, we had the epimorphism from above. So psi is onto, and we get all cosets of H, all left cosets of H over here, as A runs through all of its possible values as elements of free group F. So psi is onto this quotient group. Of course, this quotient group is isomorphic to H itself. We then have, I need a few details on the following claim. We've got psi mapping G to H is an epimorphism as required, an onto homomorphism. First off, actually psi mapped F mod n to H mod the trivial group. It mapped this to that. So technically, and I've followed Hungerford's wording of this, but there's a couple of loose ends here I want to chat about. Psi really needs to take in elements of F mod n. From there, we need to produce elements of G. Oh, sorry. Let's see. I need to start with G, get the isomorphism to F mod n. Then we had the psi as defined above, mapping F mod n into this quotient group, and then there's a little isomorphism that takes us to H. So strictly speaking, it's not psi itself that does this, but psi composed with a couple of isomorphisms. What psi does is it takes F mod n to this quotient group. So we'll start in group G, use an isomorphism to get us into F mod n, use psi to get us to H mod 0, and then another little isomorphism to get the H out. That's actually technically, that's the epimorphism we're dealing with. So this is a touch oversimplified, but the argument's valid in that there exists an epimorphism mapping G to H, and that's what we were asked to verify. So let's talk about this von Dijk chap briefly, and then we'll look at some applications or some implications of that result. Theorem 1.95 is named for Walther von Dijk. There's his dates. Hungerford has precious few typos in it. They refer to him as Van Dyck, so that's not quite right. Little research on the internet will turn up the accurate name. He was a student of Felix Klein's in Munich. In addition to his result on group permutations, he made contributions to function theory, topology, potential theory. He was involved in the creation of the German Museum of Natural Science and Technology, which had interactive displays of various scientific principles. These displays were the first of their kind and soon copied around the world. So, we used to have in Johnson City the hands-on museum where you could play with the material in the museum, interact with it. So what an oddball thing. Von Dyck, this mathematician, was involved in the first introduction of such displays in museums. He was also part of a project to publish the complete works of Johann Kepler. And this information is from an excellent place for history of math. References, as I've used many times in these notes and my other notes as well. The University of St. Andrews biographical webpage. The notes have links built in, so you can go straight to Von Dyck's biography at St. Andrews just by clicking the link in the notes. Now, let's use this theorem. First, that thing about the biggest group. Here's a relatively easy example to illustrate that. Let set X consist of a single element B, and set Y consist of B to the M. That is, we have the relation that B to the M equals the identity. That's what it means to have a word in set Y. This is not the last time we'll use exponential notation here. Strictly speaking, the way things have been set up, we were requiring the exponents to be plus or minus 1. So instead of writing B to the M with what we've had in terms of reduced words, we'd have to write that as B times B times B M times. Well, we're going to shift gears a little bit. Fraley, you'll recall me saying Fraley allowed integer exponents in his work with this, but we're going to shift over to some exponential notation for the remainder of this section at least. So B to the M equals the identity is the implication there. Then the sets X, Y give a presentation of the integers mod M as to be shown in exercise 1.9.9. A little bit of work to be done there. Of course, the integers mod M satisfy this, but some other groups satisfy this as well. So there's a bit to be shown that the group presented by that in terms of the free groups and the quotient groups and all of that is described really in that third note. There's a bit to show that this is exactly what we're dealing with. For example, if M is even, another group generated by X, which also satisfies the relation B to the M equals the identity, is a group Z sub M over 2. Now, that'll satisfy that as well. Remember, Von Dyck's theorem says, well, then there must be an epimorphism from the actual group G, given by the presentation, to this other group H that also is generated by set X, and also the implied relations, this relation is satisfied by the elements, the generators. Yeah, that epimorphism simply takes Z sub M into Z sub M over 2, mapping the equivalence class containing X to the equivalence class containing X mod M over 2. So we get a 2-to-1 mapping. Of course, there's twice as many elements of Z sub M as there are Z sub M over 2. But there's explicitly how the epimorphism comes in and how we get the largest possible group. It's finite here, so we are talking largest possible group. As in the previous example, we'll use exponential notation. We'll allow integer exponents as commented, as Fraley does. Hungerford mentions, quote, the sort of ad hoc arguments that are often the only way of investigating a given presentation. All right, so we'll illustrate that. We can find groups that satisfy the fact they're generated by set X and relation R is satisfied. Part of the trick will be How do you know you found the biggest group? Just if I find a group that satisfies that, how do I know it's the biggest group in the sense of von Dijk's theorem? And how do I conclude that actually is the group that's generated by that presentation? Well, one way, when we got finite groups, is simply to make a cardinality argument. Let X be the set A and B. So we're looking at a group generated by A and B, two generators. R is the relations. A to the fourth equals the identity. A squared, B to the negative 2 equals the identity. AB inverse equals the identity. Of course, just get used to the notation. Set Y would be that element, and that element, right? Those words, I guess I should call them words, based on the symbols X in set X, the symbols A and B. And then we take those words and set them equal to the identity. That's where the relations come from. Exercise 1.4.14, a few sections ago, shows that the Quaternions, Q sub 8, is a group of order 8 generated by the elements A and B that satisfy those relations. Quaternions can also be dealt with not as a finite group, but as something bigger. If you look up quaternions, you're apt to see that they're an example of a non-commutative division ring. Okay, well, if they're a ring, then they got two binary operations. And in some sense, that division ring is based on this group of order 8. That's an infinite dimensional, an infinite cardinality ring. And we're only talking about a group of order 8 here. But the quaternions we're interested in at this stage is that group of order 8. So it's been established, we'll take it as given, that Q sub 8 satisfies the fact that it's generated by two elements and these relationships are satisfied. So we know by theorem 1.9.5, by von Dijk's theorem, there's an epimorphism phi that maps G to Q8, the quaternions. So the cardinality of G, the group actually generated, or the group actually presented by set X and corresponding set Y, cardinality of G must be greater than or equal to 8, because here's a specific group that satisfies those conditions. Von Dijk's theorem said, well, the group determined by the presentation has to be greater than or equal to 8 in cardinality. So what we're going to do is show if these relations hold, and this is a set of generators, then we're dealing with a group of order 8. So that's how we'll draw the conclusion of equality here. G is generated by A and B. So we know by theorem 1.2.8, we've actually used this quite a bit, that the elements of the group generated by A and B are always of the form integer power of A times integer power of B times integer power of A, and so forth. It's a product of powers of the generators. We wouldn't have power of A times power of A, those we could combine. I don't know that it starts with powers of A, maybe it starts with powers of B. Fine, I'll take that first exponent to be 0 because it said they're integers. But every element of group G can be written as a product of powers of A and B. I can group the A's together and group the B's together if they're side by side. We didn't have anything that gave us commutivity. The quaternions are not a commutative group. There was nothing here about AB equals BA. AB inverse equals the identity, but still that's not AB equals BA. So we know elements can be written in this style. One of the relations we were given is that A to the fourth equals the identity. Another relation we were given was A squared B to the negative 2 equals the identity. That's A squared B to the negative 2 equals the identity. The second relation, we'll use the third one shortly here as well. So if we get a squared b to the negative 2 equals the identity, that could be rewritten as a squared equals b squared. Let's take the b to the other side, you know what I mean? We could square both sides effectively to produce a to the 4th equals a b to the 4th, also equals the identity, because a to the 4th equals the identity. So if we've got powers of a's and b's, and it looks like a and b, when raised to the 4th power, produce the identity. That means the order of these elements are 4. No, it means the order of those elements divides 4. So it's either 0, 2, 0, 1, excuse me, 1, 2, or 4. It ain't 1 because these are not the identity elements. But that means these exponents up here, we can, without loss of generality, take those exponents to be between 0 and 3. Because when I hit a power of 4, an exponent of 4, these both reduce down to the identity. And indeed, A will have order 4, as we'll see. Since the third relation was AB inverse equals the identity, we can rewrite that as BA equals A inverse B. Okay, let's see, multiply both sides on the left by A inverse, eliminating that. Multiply both sides on the right by B, eliminating that, and that'll produce the A inverse B on the right-hand side. Well, if A to the 4th equals the identity, then the inverse of A is A cubed. Usual behavior there. So we've got BA equals A cubed B. So that's implied by the relations, and that's pretty useful. That takes B's on the left and A's on the right and turns it into A's on the left and B's on the right. We've done this before. Well, it's not commutativity. It does allow us to move A's and B's from left and right to right and left, respectively. Okay, some exponents change, but these exponents are not too badly behaved. Without loss of generality, they're 0 through 3. So if we have any product of powers of A's and B's, we can one by one move the B's to the right of the A's, get the A's on the left, the B's on the right. Okay, it looks like when we do that, A is replaced with A cubed. Reverse the orders in a sense. So you picked up some factors of A squared along the way. Anyhow, that means every element of G is of the form A to the I, B to the J. Get the A's on the left, the B's on the right. Some power of A, some power of B. We've already observed those exponents may as well be 0, 1, 2, and 3 because A to the 4th is the identity and so is B to the 4th. That information alone would tell us then group G has at most 16 elements, but we're not quite done. We want it to have 8, so we need to make a somewhat more of an argument. It's the fact that B turns out to be of order 2. We've got A squared equals B squared, as given here. If J equals 2 or 3, then we can replace B to the J by A squared, B to the J minus 2. I mean, A squared equals B squared. So certainly B to the J is the same as this. So if we had B to the power 2 or the power 3, we could rewrite it as B to a power 0 or power of 1 and pick up 2 more A's. You don't need anything but B to the 0 power or B to the 1 power. You got B to the 2 or 3 power, change it into this. Change it into A's. Change part of it into A's. That tells us then that every element of G is of the form A to the I, B to the J, where the A's can have exponents of 0 through 3, and the B's only need exponents of 0 and 1. Every element of G can be written of that form. That tells you that this group G has at most 8 elements. So we cut it in half from the previous argument. But we already know that G has at least 8 elements by von Dijk's theorem. We already knew the cardinality of G was greater than or equal to 8. We've just argued because we know the forms of the elements of this group. So we use the fact it's got 2 generators, and we use the relations to arrive at this conclusion. So it must be G has precisely 8 elements. That epimorphism phi that mapped G to the group Q sub 8 must actually be onto, because they're the same size. So it must be actually 1-to-1 as well. It's an isomorphism, and G is isomorphic to Q8. So there's one way to establish that a presentation gives you a specific group. This is a presentation. I go and extract that Y to put it in the correct notation, but this is a presentation of that group of order 8, the Quaternions. We had mentioned this along the way. In exercise 1.9.8, XY, where X is the 2 generators A and B, and Y says A to the N equals the identity, implies A to the N equals identity, B squared equals the identity, and AB equals the identity, provided N is greater than or equal to 3. This is a presentation of the dihedral group. This is somewhat how we define the dihedral group. The A's, A to the N equals the identity. Remember, dihedral group is symmetries on a regular n-gon. The A's are the rotations of the regular n-gon, and the B's are the mirror reflections. B squared equals the identity. We actually defined the dihedral group somewhat like this. We were dealing with it as a subgroup of S sub n at the time. So we said it's a subgroup of S sub n generated in a certain way. That's the thing with the group presentation. We're not dealing with a subgroup of anything. We're building these groups out of generators and relations. And the generators and the relations and this theory we've developed of free groups on a set is what allows us to produce those groups from this kind of minimalist amount of information, I suppose. Speaking of free groups, let X be a set, a non-empty set of generators, and suppose Y is the empty set. Then, if we look at the presentation, XY, it's a presentation of the free group F on set X. The group's free in the sense that there's no relations imposed on the generators of F. I don't exactly know the history of this, but I rather suspect that's why free groups are called free groups. This presentation stuff probably comes first, and then we're putting no relations, no constraints on the generators. So allowing the generators to be free in that sense. We would look at this in terms of F mod n. Look at note 9.1.3, where we dealt with the free groups. F mod n would be the kernel of homomorphism. Well, that would consist of the identity. I don't necessarily have anything else that produces the identity in terms of generators. So we've got that freedom. We get F mod n is the same as F mod a trivial subgroup, and that's F itself. So you get the isomorphism, you get the free group out when we have no relations. Another comment about this, possibly we've mentioned in the past, or you've been exposed to this idea of dealing with finite groups. We mentioned this, at least in passing, in the context of finite simple groups. There's a book out there by Conway, Curtis, Norton, Parker, and Wilson called The Atlas of Finite Groups. It's actually the fonts they use in the title. Dates from 1985. That's like the size of a newspaper. It's this giant red book, spiral bound, that gives presentations of various groups. These days, there's an online version out there with probably all the same information with corrections. I know there were some typos in the first edition of this thing. The eTissue library actually has a copy of the first edition. But this web page, if you like, gives a presentation of the group M11, the Mathieu group. I have some notes out there. I know we've mentioned this before on finite simple groups and how they relate to finite groups in general. We can classify finite simple groups into a bunch of categories, and there's a handful of sporadic groups, they're called, left over. The Mathieu group is one of these. But this group M11 is of order 7,920. So if we wanted to discuss the Mathieu group M11, if we made a Cayley table, that'd give a complete description of it, but that'd take 7,920 squared entries. So something like 63 million entries. But there's an easier way to present this group. The online atlas gives a presentation of M11 as, it's got two generators A and B, and here's set Y that determines the relations. A squared equals the identity, B to the fourth equals the identity, AB to the 11th equals the identity, and this thing here to the fourth power equals the identity. All right. Establishing the order of the group, well, theoretically, probably pretty much the way we dealt with establishing the order of the dihedral group, or for that matter, the order of the quaternions, the group that was generated a couple of examples back that turned out to be isomorphic to the quaternions. I suspect we do an order argument somewhat similar to that. But the point here is, yeah, there's a presentation of the group, and that beats the hell out of having 63 million entries in a Cayley table. So it's a concise way to present groups. Simply from the presentation, though, I can't look at it and tell what the order is. I can't tell much at all, simply given the presentation. But it does fully describe the group, in theory at least. Note 1.9.3. This presentation does determine some group. Properties of that group are to be determined, I suppose, but it's a clean way to give a presentation of the group. So we're going to shift gears a little bit and go kind of light on the details, as it says. Let's look at coproducts in the category of groups. The constructions are really similar to what was dealt with in terms of free groups. So we're done with proofs, but let's get a little bit more vocabulary out there and a couple other little ideas. So we'll take a family of groups, G sub I, as before. We may assume that the G sub I are mutually disjoint sets. So we're going to take these elements of these groups and treat them as letters when we do the free group thing, when we make words. So I need all these groups to have different letters. For example, we'll have to make the identities something different in each group. So given a family of groups, we'll assume in what follows that these groups form mutually disjoint sets. So the definition to follow says, let G sub I be a disjoint collection of groups, as we just described. Let set X be the union of the elements of those groups, and let one be a one element set disjoint from set X. So we're throwing that symbol in. Don't use one in any of the G sub I's. So we're taking X to include all elements of all of the groups and this symbol here. Previously, we had a set X inverse. Well, you've got all these elements of the groups. They'll come with inverses. Right? Set X will contain the inverses in a group theoretic sense. So we've got set X. We've got the symbol 1. A word on X is simply a sequence, A1, A2, such that each A sub I is from the set X or is the symbol 1. And for some natural number, we have A sub I equals 1 for all I greater than n. Usual thing, it ends with all ones. These are technically infinite sequences. They are pragmatically, they're finite sequences because they end with an infinite number of ones. So we could run over and drop the tail, snip that off, and treat them as if they were finite. And of course, that's how we'll manipulate them as we did in the past. Word A1, A2, and so forth is said to be reduced, provided no A sub I is an identity element from whatever group it's from, right? Says group G sub J. Yeah, the positions don't correspond to the groups in any way here. I mean, this is a nice little countable sequence. We could have an uncountable number of groups. There's not a group G1 and a group G2. That's not what we're doing here. There's a kind of a first letter and a second letter and so forth. We're saying don't use the identity element from any of those groups as one of the letters if you want a reduced word. For all I and j, we have that A sub I and A sub I plus 1 are not in the same group, say G sub j. So we wouldn't have two consecutive elements from the same group in a sequence. We could always multiply them together because they come from the same group, and that's how we'll do the reduction. And A sub k equals 1 implies A sub I equals 1 for all I greater than or equal to k. So as soon as you get a 1, it's 1s from there on out. So if we wanted to reduce, we wouldn't use identities, we just throw those out. We wouldn't use 1s until it was all 1s. So we'd throw any 1s that might initially appear out, except on the right-hand tail of the sequence. And if we had two terms from the same group, maybe if we were doing some juxtaposition, we'd simplify that. And that's what we'll describe below. The word of all 1s is reduced. And every reduced word other than that one may be written uniquely as A1, A2, up through A sub n. It represents the infinite sequence that after that A sub n is all 1s. The uniqueness coming from the way we'll reduce these words, as we're about to see. Okay, let's try to get all of this on the screen at once. We're in the process of defining what we'll call a free product. So to give me something verbal, I'll just go ahead and call this from the beginning the free product. Notice it has a little asterisk up top instead of like a W when we dealt with weak direct products. But let the free product be the set of all reduced words on X, as described previously. If I is finite, we denote this G1 star, G2 star, so forth up through G sub n. Define a binary operation on the free product as follows. 1 is the identity, so anything times that word, that reduced word, yields whatever we multiplied it. W times 1 equals 1 times W equals W for all reduced words, right? So make that the identity. That defines the binary operation on 1. And the product of two reduced words, other than 1, is the reduced word, which results from, you know, what's coming next, from juxtaposition followed by reduction. So we'll place one word after the other and then make sure we get a resulting reduced word. If juxtaposition puts an element of G sub I next to its inverse, eliminate those two elements. If juxtaposition leads to two elements of a given G sub I next to each other, replace this pair with its product in that group, G sub I. So simply place one word after the other, one reduced word after the other, and the right-hand end of the word on the left and the left-hand end of the word on the right, where they meet up, fix it if it needs fixing. To be quite informal, the result is called the free product of this family of groups under the binary operation. Quick little comment at the bottom of the page here. It really is a group. We'll state without proof the fact that the free product of a family of groups actually is a group under the binary operation that's described. To illustrate it, Hungerford gives this little example here. Take 3 groups. G1, G2, G3, and A sub i's and B sub i's from these groups, G sub i's, and consider word A1, A2, A3 times word A3 inverse, B2, B1, B3. So we've taken the words and juxtaposed them. Oops, there's an A3, A3 inverse. Well, we need to fix that. So that produces an identity. We'll just eliminate those two. When they're gone, then we got an A2 over here and a B2 over there. Well, they both come from group B2. So we'll need to combine the A2 and the B2. So we're going to write this as A1, C2, B1, B3, where C2 is the product of the A2 and B2. So we kept the A1 up front. We kept the B1, B3 on the right-hand side. And these four terms simplified down to what we represented as C2. First, A3 inverse, gone. Eliminate that. Then we need to account for the A2, B2, this A2, this B2, represent as C2. Perform the multiplication in group G2, whatever the product turns out to be, represented with a single element. And that produces this. This is a reduced word. We don't have consecutively two letters with the same index. So these come from different groups consecutively. There's no ones anywhere inside. Of course, that's shorthand notation for the series that's got ones as a tail. So there's a definition of a free product of groups. Following result shows that the free product actually is a coproduct in the category of groups. Not to belabor this too much, but saying we had a either product or a coproduct always involved the existence of a unique morphism. Here, the morphisms will be homomorphisms in the setting of groups. So Theorem 1.9.6 says, if G sub I is a family of groups, we consider their free product. If psi sub I is a family of homomorphisms mapping, psi sub I maps G sub I into H, so we're given some group H, and a family of homomorphisms, psi sub I. The claim is there exists a unique homomorphism, psi, mapping the free product into group H, such that psi composed with the inclusion map equals psi sub I. Homomorphism, unique, satisfying this composition condition. We've done this before. Every time we made a claim about product or coproduct in a category of groups, it was something of that sort. And this property determines the free product uniquely up to isomorphism. In other words, the free product is a coproduct in the category of groups. And that's it for the material. I do want to make a handful of comments. For final comment on group presentations, let's briefly address what's called a group isomorphism problem. The problem is to determine if two finite group presentations represent isomorphic groups. It was introduced by Max Dehn in 1911 on infinite discontinuous groups. Dehn also introduced the quote-unquote word problem and the quote-unquote conjugacy problem in that same paper. The word problem is to decide whether two words written in terms of the generators of a group represent the same element of the group. The conjugacy problem is to determine if two words X and Y in a group, if there is Z in the group such that Y equals X conjugated by Z. Y equals Z, X, Z inverse. All three problems, the word problem, the conjugacy problem, and the group isomorphism problem, all three problems are undecidable in the following sense. There does not exist a computer algorithm that correctly solves every instance of these problems, regardless of how much time is allowed for the algorithm to run. So there's no finite way to describe how to determine the answers to these questions about equality or isomorphisms. This information is from maybe not the soundest source in the world, but it's from the Wikipedia page on the group isomorphism problem. They do give reputable references there. The undecidability of the isomorphism problem was given in 1958 by two folks, Ajan and Rabin. The results now call the Ajan-Rabin theorem, the fact that this is undecidable in the sense stated above in terms of the existence of an algorithm. Reference on this and related problems concerning undecidable problems in group theory is given by Sacardo. I should have practiced this in my mind more. Sacardo's paper that appeared in the proceedings of the AMS. These last two papers, I've given links. They can be previewed. That means you can see the first page. So it includes the abstract and the reference. JSTOR has the first pages of these available. You can get to these if you use your ETSU credentials, though. You can log in using your ETSU credentials into the ETSU library, and we subscribe to JSTOR, and you can see the entirety of these papers. Anything by the AMS, ETSU is an institutional member, anything by the AMS, the American Mathematical Society, you can get access to it if you go through the proper protocols. A more detailed discussion of group presentations can be found, so you might not have seen this coming, in Chapter 4, Presentation of Groups, in Introduction to Knot Theory, kind of a foundational book in knot theory by Crowell and Fox. It's been in print since 1960s. Dover still has it in print. It's available as a little inexpensive paperback Dover book, a couple hundred pages. It's not that big. If you'll poke around online, you might find a copy of it in PDF as well. But this comes up in the setting of knot theory due to the fact that a group can be associated with a knot. And a physical knot, what you might think of is take a piece of string and twist it around itself a certain number of times and then join the ends. Knots are closed curves in that sense. But it turns out to be quite difficult to determine if two knots are the same, equivalent. Equivalent in the sense that without cutting it and untying it, one knot can be transformed into another. If you're somewhat familiar with this, equivalence can be described in terms of three little moves called Reidemeister moves. But it's difficult to determine when two knots are equivalent. One way to determine it is to associate a group with a knot, and in so doing, up comes group presentations. Group presentations naturally arise when associating a group with a knot. If we look at two knots and we wonder if they're actually equivalent, well, if their associated groups are different, then not isomorphic, then the knots are not equivalent. But there's a kind of a application of group theory right there in the setting of knot theory, of all things, an algebraic way to approach knot invariants. There's other geometric ways to approach them as well. But that takes care of group presentations, takes care of free groups, free products, generators and relations. Really, it's the group presentation stuff that catches my eye the most in all of this. And it was done in terms of the free groups. So that's why free groups pops up, and then the discussion of group presentations. And that takes care of Chapter 1. So have a nice day. We'll pick up in Chapter 2, and I'll see you there. Bye-bye.